I don't want to prolong more, because Sugesh sir has already given a very good introduction, and Babaraj sir augmented that. So I think you are very eagerly waiting for the session. So as a formality, I'm declaring that the FDP, the 6-day ATAL online FDP on smart energy storage technologies from research to real world application is inaugurated. And I hope that all of you will enjoy this particular program, and we'll have a continuous interaction even after this particular course. Thank you very much.
Thank you, Sri Kumar sir, for inaugurating the session as well as motivating us with the very positive statements. Thank you all. So we are actually we have reached the timing is 6:28 now. So in a 2 minutes time, we will conclude the session so that we can keep the timing everything intact. So I invite Professor Akhil Chako for the to give the vote of thanks to the team. Professor Akhil Chako, thank you.
Yeah, good evening all. Hope I am audible. So, respected Principal Dr. Srikumar sir, HOD Babaraj sir, Sugesh sir, other faculties of Triple Department, and my dear participants. So, as we have come to the end of this inaugural session, I would like to take a moment to express my sincere thanks to everyone who made this possible. So I sincerely thank our respected Principal Srikumar sir and HOD Babaraj sir for their constant support and encouragement. I would also like to thank all our resource persons for kindly accepting our invitation and being part of this FDP. Again, a special thanks to all the participants from across India who have shown interest and joined us today. I wish everyone a very fruitful and engaging FDP ahead. Thank you all. Now, without further delay, I warmly invite our esteemed resource person, Dr. Manojkumar MV, to take over the session. So, Dr. Manojkumar MV is a distinguished academician and researcher in the field of electrical and electronics engineering. He is currently serving as Professor, Department of EEE, Government College of Engineering, Thrissur, with extensive experience in teaching, research, and academic administration. He completed his BTech in Energy Science and Engineering from IIT Bombay and earned his PhD from IIT Madras with specialization in the application of power electronics in power system. His research interests primarily include power system, renewable energy integration, smart grid technologies, and advanced electrical engineering application. He has made significant contributions through research publication, funded projects, and academic mentoring. So I warmly welcome Dr. Manojkumar MV for today's session and wish all participants a fruitful and enriching learning experience. Thank you. Over to you, Dr. Manojkumar, sir.
Thank you, Akhil sir. Thank you all. Good evening to all of you.
Manoj sir, in between, just a small announcement. Kindly participants, please mute your Google Meet so that there is no hindrance to the presentation. Thank you.
Okay. Thank you, Sugesh sir. Let me share my screen presentation. Hope it is visible. Presentation is visible.
Yes, sir. Yes, sir. Yes.
Okay. So, very good evening to all, and thank you for the organizer for inviting me for presenting a topic in this FTP. The topic what I am going to present today is the basics of energy storage system. Just listing out the different types of storage, what we are available right now. And some of the application of these energy storage systems, mainly in the case of microgrid. So coming to the summary of presentation, going to the introduction, basic classification, not going to the details of energy storage system because you have many, I think 2 more session which will be describing mainly on the material side and also the basic types of this type of energy storage system. Then some combination of different energy storage system. We can call it as a hybrid energy storage system. And some of the different power electronic converter method, converter topologies for the control of this type of hybrid energy storage system. What we have done as the different projects or in our college itself. And then about the modification in the control when a high battery energy storage system, say heavy size of the order of say 100 megawatt hour or 150 megawatt hour. So this type of heavy battery energy storage systems are connected to the grid side. An energy efficient control method is also will be discussed. So coming to the introduction, as you all know, a microgrid, the essential component is the energy storage. That will actually help to operate the microgrid in different modes of operation, like grid connected mode or isolated mode of operation. Now, if we take these 2 mode of operation of a power system, you can see that the importance of these energy storage units, or briefly ESS, in some aspects it will be compensating mainly the intermittency caused by the renewable based power system. You know that mainly when we say the microgrid, the majority or the major share of the power source will be from the renewable source like PV or wind, which are intermittent in nature. So this can be compensated, or it can be, the intermittency can be somehow regulated by using this type of energy storage system. So that is one of the important. It is applicable for both the grid connected as well as islanded mode of operation or isolated mode of operation, because in some cases, I will tell you the practical case of the Kerala power system. Kerala power system, here the state electricity board has recently planned to implement battery energy storage units, because here the generation of power from the intermittent source like PV is somewhat increased in the recent years, and in order to mitigate the issues related with the intermittency, in nearly 5 or 6 localities, the state electricity board has planned to install this, and it is almost at the finishing stage. And one type of that system is having around one which is placed at the northern side of the Kerala. It is having around 125 megawatt hour capacity, or in terms of megawatt, it is around 500 megawatt capacity. So that is the case. So the one of the important point related to the storage, when we say either in islanded mode or connected mode, it is to reduce the intermittency caused because of the renewable based power system. And additionally, in the existing power system also, because of the variation in the power generation from this type of renewable based source, because the penetration level of these power sources, renewable based power sources, has increased much. It has come to around 20-21%. So at the level of that renewable based power system has increased, there is a little bit stability issues related to the voltage as well as the frequency. And it is clearly visible nowadays in the distribution system. Sometimes, if you look at the, we have conducted one case study where for a distribution system where the where they have installed instead of a consumer, it is producing power of around 5 kilowatt, and we observed a voltage level of around 260 volt in the LT single phase system. So during the daytime, so that type of voltage stability issue is there. It is not getting controlled even though the inverter has the capability to control the voltage. So that is the case of distribution system where there is a power generation in the small home. We call it as a solar home, like that. So there also, in addition to the distribution system in in other higher level distribution system also this type of issue can come. So the second purpose is to maintain the voltage and the as well as the frequency stability. Then with the use of energy storage units, if it is properly designed and sized, it can supply the power even if the grid is in isolated mode or islanded mode. So that is the third important, that is the enable islanded operation. And even if the grid failure, even if grid failure comes or blackout comes, the starting can be independently done. So that is what the black start does. So the independently isolated power system can start and it can be connected back to the power system. So that provide a black start capability. And another, by properly planning the energy storage, it can perform the peak shaving as well as load leveling. So the entire load curve of a given state or a district or an industry is getting levelized, or the load factor is getting improved. So that again gives some is some form of a demand side management. It is getting an improved power system. And additionally, the power quality also can be the same type of converters or the whatever the power electronic device what we are going for, what we are using for integrating this type of battery unit to the system, say grid. The same converter can be used for improving the power quality, or even by simply by maintaining the voltage and the frequency by using a specially designed or the it is designed battery energy storage system. It is actually improving the power quality of the system. At the same time, the same converter also can be used for improving the power quality. So that is why these are the main importance are listed here. So with this in mind, some of the aspects will be discussed here as the case study or the projects that we carried out, and some general points are given here. About the classification of energy storage system, we have a long back. It is being used for the first type of energy. It was the energy storage system which was used to flywheel energy storage system. Flywheel energy storage system, if you look at it, is having a high power density, but the duration during which it can supply, the amount of power can supply, it is very large, or it is having a fast response, or you can say the energy density is less. So it is used for normally regulating the frequency or some supplying a dynamic type of load, or which lasts for a very short duration. Then about the pumped hydro energy storage is there. So there, if the power demand is very less, then during that time the energy generated is utilized for pumping pumping water back from the tail race to the dam, and thereby again it is the capacity is getting increased. So that is this type of small pumped hydro storage also there. So it is having actually large capacity, efficiency also good, but it is specifically, it is a site dependent. It is wherever it is available, it can be applied. Then about the compressed air storage is also another form of energy storage system. There also, based on the size of the units, compressed energy storage unit, it can be bulk or it can be altered also. So that depends on the capacity, depends upon the size of the unit. But if we look at the overall efficiency, that is converting the energy to the air or energy of the compressed air, then taking back from the compressed air, back energy from the compressed air. The overall round efficiency, if you look at it, is very, very low. Then comes the electrochemical type of energy units. The popular one, which is mainly used for microgrid, is the lithium-ion battery. It is having higher efficiency and it is available in many range, higher range also. The response is also comparatively fast, but the cost is very high, so we have to look into that. Then about the lead acid batteries, low cost, shorter lifetime. As in the welcome speech, Sugesh sir said that the cost, it has to be replaced 7 years or 8 years when we couple this type of energy storage system for any type of renewable based power system. So then another topology, another technology, another classification based on the technology is the flow battery. So wherein what it is done is the electrolyte is kept separate as a separate container. So the flexibility you are getting is the container size can be changed. So that actually changes the total watt-hour capacity or kilowatt-hour capacity of the battery. So there is a flexibility in changing the size of the system, size of the storage unit. So that is the flow battery unit. Then comes the sodium sulfur batteries. It is having high energy density, but the temperature of operation is somewhat higher. So some method has to be adopted for managing the temperature. Then comes the electrical storage unit, mainly the supercapacitor. Supercapacitor, you can see if we look at the recent publication, many papers are there describing the use of supercapacitor for microgrid application mainly. They have the advantage of they are very fast charging as well as discharging. But the content of energy in it is very low. So we say no low energy density device, but the instantaneous energy or the power is very, very high. It is it can be charged or discharged at a faster rate. Mainly used for transient supporting or supplying a transient type of load. And another type of energy unit as the technology is considered is the superconducting magnetic energy storage, very high efficient, but the cost is the one of the major drawback of higher cost is one of the major drawback. So the people have taken in different types of source depending upon the application, depending upon the availability. Hello, hope it is audible. Is there any noise coming in between? No. Hello.
No, sir, it is clear.
No, it's clear. It's fine. Okay. So the people have used, instead of a single source of energy storage system, they have tried combination of some of the energy. So the as far as the electrical engineer is concerned, or microgrid application, when we look at which is having a load which is varying in nature, they found that the suitable combination will be the combination which can supply a sustained form of energy and also a source which can supply a dynamic nature of energy, or which is having a source which is having both the power density as well as high energy density. So they go for a system which is a combination of a battery and a supercapacitor. Okay, so we'll be discussing in the coming slides about a system which is a combination of a battery and supercapacitor supplying load for a particular application, and the different simulation and whatever the hardware results will be presenting in the coming slides. So this is the basic overview. The details we will be seeing we'll be discussing in the coming, I think, the coming section. About the supercapacitor, what they did is in the normal capacitor, we have a plant near to in the Kannur. They are producing the Keltron, company called Keltron. They are producing supercapacitor varying from different capacity up to they tried up to the level of 500 farad. They tried, and they are trying to increase it to 3000 farad. So the idea is in the normal capacitor, the material side, you have one more session in this material aspect of this supercapacitor manufacturing aspect and all. There, what they did is they have decreased the size of the electrode. So obviously, the capacitance, if you take the case of a parallel plate capacitor, it is a epsilon 0 epsilon r into A by D. So by decreasing that D value, the capacitance can be increased, but it limits the voltage that it can handle. So the value of voltage that is obtained in the present scenario is only 2.7 volt. There also research is going to increase the level of the voltage of a one capacitor unit, supercapacitor unit. So presently it is at 2.7 volt, and they are available in the range of starting from 5 farad, 18 farad, 15 farad, then 500 farad, 3000 farad, etc. So obviously, for getting a higher level of voltage, you need to connect many cells, many supercapacitor in series, and for increasing of capacity, some are connected in parallel. So some combinations are there. So basically, if we look at the theory, see the basic point related to the supercapacitor that I highlighted in the slide is the comparison between the battery and supercapacitor. As I said earlier, battery is having a high energy density, so it can store a load based on the size of the battery. But the power density is slow, so it delivers slowly as compared to the supercapacitor. On the other hand, the supercapacitor is having a low energy density, but it is having high power levels. So the combination, it is combined together to get the advantage of both. The main advantage for this type of supercapacitor is a long life cycle, and fast charge and discharge, as already mentioned. It is if you are comparing this with a capacitor. Capacitor is having the specific energy density, that is the amount of energy it can store per kilogram. That is very less only, but it is for supercapacitor is somewhat higher than that, but it is lower than the battery. It is in the range of 1 to 10 watt-hour per kilogram. Similarly, the specified power density is also listed here. And another main issue with, as I said, supercapacitor is having a voltage limitation. It can once SC is having only 2.7 volt. Additionally, there is one more issue with this. If we keep a supercapacitor as it is without connecting to any voltage source or without drawing any current, there is a leakage of self-discharge of the supercapacitor, or the leakage of current through that. And it is denoted by a term called DCL of a DCL. DCL, it is called DC leakage. So it is there for all supercapacitor. So that actually reduces the overall Coulombic efficiency of the supercapacitor. So if you take the discharging capacity divided by charging capacity, it lies in the range of 85 to 98%. And as I said, supercapacitor is having high charging and discharging duration, or sorry, the small charging or the rate, it is faster, but it is compared to supercapacitor, it is lower. Sorry, compared to capacitor, it is lower. So the value is given here. Supercapacitor is 0.3 to 30 seconds, and for capacitor, it is 10 to the power minus 6 to 10 to the power minus 3 seconds. And we have done the charging and discharging in the charging and discharging of the capacitor and the supercapacitor in the lab, only to get a feel of these. It is actually obvious the normal capacitor waveform is shown in A and B. They are no charging waveform is given in A, figure A, and the discharging of the capacitor is shown in B. So it takes depend upon the capacity of the capacitor, normal capacitor. And as compared to this, for supercapacitor, we are done for around 5 microfarad, sorry, 5 farad capacity, and it takes a longer time to get final voltage, final rated value voltage. If we look at the discharge pattern, if more loading is given to a supercapacitor, it discharges very fastly. So that characteristic is shown in the discharging profile. So if it discharging profile for 20, 40, and 60 ampere are given. So the 60 ampere for 60 ampere is supercapacitor discharge very fast. So this is making use this property is getting useful or in the application of a microgrid system when we go for hybrid based or hybrid energy storage based microgrid. This is the standard rating of supercapacitor available. This is the data sheet of a Credtron. The main data what we are interested while using this for a particular application is, one is the capacity, and then see the peak current it can supply. A 500 farad capacitor, supercapacitor can supply 80 ampere peak current. 80 ampere peak current shown in the last row of the table. Additionally, the continuous current it can supply is 25 ampere. It can supply 25 ampere continuous current also. The term that I mentioned earlier is called DCL. DCL is given in one column. So that is the DC leakage. So that is DC leakage is order of microampere or milliampere. And for 500 farad capacitor, it is the order of 1.1 milliampere. And why we are interested in here is, if we use this for a particular application, the 1.1 milliampere indicates that we need to supply 1.1 ampere continuously to maintain the voltage of the capacitor. Otherwise, the supercapacitor terminal voltage will come down. So some mechanism, some control method has to be there in the system, in the overall unit to maintain the voltage. Means this 1.1 has to be injected, 1.1 milliampere current has to be injected continuously from some other sources. Otherwise, the system voltage may come down, or means supercapacitor voltage will come down, or the DC voltage what we are interested, or the DC link voltage will be getting reduced. So the other data, it is available with the Credtron data sheet. We will share the reference of that also. So that is about the supercapacitor. So with this, that is with these in mind, that we have one battery energy storage system or simple battery units. Then we have a supercapacitor. They are complementing the property to each other. So basically, we are combining these two for a particular type of application in a microgrid. And mainly, it is suitable for application where there is a frequent change of loads, frequent change of where it requires starting, stopping, or change of load pattern, etc. So we consider one load. That load I am not mentioning because that is not at all importance here, and that is supplied from one type of a power electronic converter, which is powered from a PV renewable based power source. So the PV is shown here on the left hand side. So that is simulated that the DC source is representing the PV, and we are using two types of source. One is called the battery source, which is shown here as VB, and there is a supercapacitor which is represented by VSC. So basically, this converter is supplying power from a PV, and that power is used for charging the battery as well as the supercapacitor. But you see that the supercapacitor nature of charging and the discharging as compared with the battery, it is different. So anyway, in this topology is not differentiating, or it is not giving any type of control to control the charging current and the discharging current of these individual units. That is, battery current and supercapacitor current are not getting controlled. They are getting controlled only because of the inherent value of some inductance used in the battery circuits. Say there is a value called the LB connected in the battery circuit. So that actually controls the value of current drawn or supplied by the different units. So the idea is here a simple circuit is used, and some power electronic switches like S1 and S2 are used. They are controlled, and they are controlling only for transferring power from the PV side to this battery or the load side, or it is like a boost converter. But the current sharing between the battery and the capacitor, supercapacitor, is not getting controlled. So that is why it is called a passive type of topology for hybrid energy storage system. It is popular. Why? Because you don't require any type of control. Control circuits is a simple topology, but it is applicable only for a specified type of load where you are already know the value of the current or the change of current or the amount of the dynamic changes coming in the quantity of the change coming in this load. Then you are easy to implement this type of topology. This topology has been built. This is actually it is built in the lab, and it is the hardware parameter is given here. It is done for a small range of voltage only, laboratory top prototype of around 200 watts only. But only to say that the nature of current supplied by the battery and the supercapacitor are different, and because of this, there are some improvement in the system or improvement in the storage units. I will explain to you the nature of the current, and what is the implication of the result will explain to you in the coming slides. If you look at the simulation results, the left side, it is battery voltage, battery current, then the state of charge, the power drawn from the battery are given, and on the right hand side, all the supercapacitor parameters similar to the battery, like voltage, current, SOC, and the battery are also given. So here, if we see the current drawn from the or supplied to the supercapacitor, it is seen that there is an instantaneous change of current supplied by the battery or supplied by the supercapacitor or drawn by the supercapacitor. While on the left hand side, you can see that in the green color, they are of a steady nature. It is a constant current is being drawn from the battery, or it is supplied to the battery during the charging. So different region of operation is given, some charging region and the discharging region. So charging region, the battery side, negative current is shown, and the discharging region of the battery is shown with a positive current. The similar pattern is given for the pattern, means a similar type of graphs are given for the supercapacitor also. This is not as fully expected. Some errors will be there. So that is the drawback of some errors, means you cannot say that you cannot fix the amount of instantaneous current taken by the supercapacitor during a transient period. You cannot say the amount of current taken by the battery during a transient period. You cannot fix it. So that is why it is called a passive type of topology. It is implemented in the lab, and the result I have not shown here for this passive topology. I will tell you another topology and another improved topology. So this is called the same type of energy storage system, that is hybrid energy storage system, can be interfaced with your intermittent sources like PV or wind system. Here it is PV is taken. So it can be interfaced, and also they can be used to supply a dynamic type of load, varying type of load by another type of combination. That combination is described here in the slide, and it is called the active hybrid energy system, active hybrid HESS topology. So the power electronic topology used is the active. Why active? Because here the amount of current taken by the battery or taken from the battery, or it is supplied by the battery, is decided by the control. In the figure, if you look at, by controlling the switches of battery side converter, it is given as converter 1 here. It is shown as converter 1 here. By controlling SW2 and SW3 of the converter, the amount of current can be controlled. Similarly, the amount of current from or to the supercapacitor also be controlled by controlling the switches SW4 and SW5 in the figure. So both are shown as bidirectional converter. So can be used for charging the battery or charging the supercapacitor, and similarly for discharging the supercapacitor and discharging the battery. And all these are coupled to a common voltage, common terminal. We call it as a DC link, where the load is connected and power is fed to the DC link by using a renewable source. Here it is a photovoltaic. So what basically the advantage of this type of system is the amount of current can be exactly controlled, and the similar setup, that is the hardware also, we have implemented actually. It is for a lower power rating of around 200 watts only. The control, I will spend some 2-3 minutes to explain the control, because there can be many modification to this so that system can be improved too much. So a lot of research are going to for controlling the current sharing or fixing the current sharing between the two sources in a hybrid energy storage system. Here it is a battery and a supercapacitor. So here the point is, by controlling the switching signal to SW2 and SW3, the battery side converter is getting controlled, and SW4 and SW5 shown in the figure, the supercapacitor side DC bidirectional converter is getting controlled. So our basic control topology is to control the signals SW2 and SW3 or 4 and 5. Okay, so to do that, what it is done is the DC reference voltage will be fixed. DC reference voltage is nothing but the voltage which is required for the DC link. Say it can be 24 volt or 110 volt or 220 volt, etc. So this is fixed, or this will be maintained at a constant value. Then this will be compared with the actual measured value of the voltage. So you require a voltage sensor for that to do the measurement of actual DC link voltage, and the sensor's output will be compared with the reference value, and this will be given to a controller. It can be any type of control you can go for. So inside the controller, the error has to be determined. The difference between the reference to the actual has to be calculated, computed, and it has to be given to a PI controller. So PI controller actually find out the amount of, or it is nothing but the amount of current which is to be supplied to maintain the DC link voltage to the reference value. So that is nothing but the I total reference. So this will be computed inside the controller, and this again the inside the controller, this I total reference may contain some, we normally say it's a steady state current as well as some transient nature of current. Why? Because this is real time in nature, so it is continuously monitoring the voltage, continuously comparing the voltage with the actual DC link voltage with the reference DC link voltage, and is given to a PI controller. So there is if there is a continuous change of loads associated with the entire system, there can be a change of voltage, or this will be reflected in the total reference current, I total reference. So we can expect I total reference as a combination of some steady value as well as some transient value. Now we need to filter out the transient value, so that what we are interested is, what our motivation is to make this value or give this transient current value to the supercapacitor and tell him to support this or to supply this transient current. So we need to filter out the two parts. We need to separate the steady state as well as the transient part of the total current required, which is required for maintaining the DC voltage. So basically, it is given to a low pass filter. Low pass filter design itself is you cannot. It is again another part of the research. So you find out this IB reference. The output of the low pass filter will be a steady state value. If we subtract this IB reference value from the total amount of current, that is I total reference, then the difference will be the transient current. And we are telling this transient current to supply by the supercapacitor. So this has to be fed to the this has to be given to generate or actuating the switches of supercapacitor, that is SW4 and SW5. Now there are some other additional changes made in this particular topology, in this particular control method, wherein in addition to the IHFC reference, that is simply by subtracting IB reference steady state value from the total reference current and getting the IHFSC reference, that is the reference current for the supercapacitor. The error is IB error is also getting added with this. Why IB error is added? Because sometimes whatever the current reference is given to the battery converter may not be supplied actually by the battery. So there can be some error which is not getting supplied by the battery mainly during the transient period. So that is also getting added with this IHFC reference, that which is not supplied by the battery is also getting added, and so it is improving the efficiency of the system. Okay, and whatever the control or the computation we made so far is by comparing the reference voltage with the DC link voltage, VDC actual voltage. And now it is getting normalized. It is getting normalized by the supercapacitor voltage. In actual hybrid energy storage system, you find that when you make a practical system, the value of voltage across the supercapacitor is somewhat higher than that of the battery voltage. Mainly, it is accounting the leakage problem. So here VSC, if we take, it is some 1 or 1.5 volt, 1.6 volt, I think it is taken here. So it is very little bit is more than the battery voltage. So in the lower, while making SW4 and SW5 switching, you can see that there is a normalization given by, it is divided by VSC and it is multiplied by VB to get the a supercapacitor reference current. Okay, so that is how. So there are many modifications nowadays coming in the literature also. So the basic structure involves you filter out the steady state component and give that steady state component of the total current of the reference to the battery and give the transient component of the reference to the supercapacitor. That is how the controlling is done. So this is done and it is implemented and it is working as per the expectation, that is supercapacitor is able to supply the transient current and the battery supply the steady state current. And the additional advantage, so we are making a storage system with the combination of supercapacitor and battery, and what it is giving is, it is actually giving or increasing the life of the battery. Why? Because the battery is supposed to supply the steady state value of current. As the current stress or the change of current is very less, the battery is able to withstand more period, or the life is getting improved. So now the scope with this is done for a very low voltage of around some 24 volt DC link voltage. That this voltage level can be actually expanded, or it can be increased by adding more supercapacitor in series. And if we look at the distribution system, we have actual power distribution system. We have a transformer, and if there is a possibility or in the future to replace the transformer with a smart transformer, or we call the solid state transformer, where the possibility is a solid state transformer, there is a provision to supply the renewable based power in DC form directly given to the DC link side of the smart transformer. So by using this transformer, this type of transformer technology are getting implemented in near future, then by increasing the supercapacitor voltage level, this can be accommodated there, and that actually gives you more benefit other than supplying this type of dynamic load. If you can supply some transient issues in the power system itself, or some transient voltage problem in the power system itself. But the only thing is the voltage level has to be increased. So that is given as the future scope of this work. And another issue coming while modularization, while increasing the voltage level, is many cells are to be, supercapacitor cell are to be connected in series. Then, as you know, the voltage level of each unit has to be equal. Then only there is an improvement in the efficiency. Otherwise, there is a localizing current in between. So that may destroy the property. Destroy is some of the cells in the, say, low voltage cell in the series connected unit. So there should be a mechanism or some circuits to make equalization of voltage across the cell also. So that is also a possibility. So what I mentioned so far is one of the application of the combination of two energy storage units, and how it can be expanded to get a better insights, or it can be a better utilization in the existing power system. And now I will be explaining to, shall I move? Any queries, any questions, any clarification is required? I'll be pointing out another application or another variation of the control strategy while integrating a battery energy storage system to the grid. So that is the next agenda what I am going to present. Is there any questions related to the points that we discussed so far, or just an interaction, or anything is to be anything more to be added?
Sir, we'll have the interaction then, sir.
Okay. Thank you. So coming to the another application of battery energy storage system. This has been mentioned in the welcome speech itself. This is a particular case of one of the district in Kerala, Kasaragod. There you have the red color. I don't know whether it is clear. The red color graph is shown. So that is the net load in the system. That is the net load. And if a separate battery energy, they are planning actually, I think 150 megawatt hour capacity battery energy storage unit, not connected, but it is almost implemented, means almost installed, not connected. I think if it is installed, it is estimated that the change of the wave load curve will be like this. It is shown in the green color. So the change will be like more power will be taken to charge the battery during the daytime, and this amount of energy storage can be utilized to supply power during the peak time. Peak time here it is shown as 18 hours to say 21 hours. So during 18 to 21, some amount of energy, that is bus discharging, it is shown like a bus discharging. It can be supplied during some 6 p.m. to 9 p.m. But the charging, it takes more power from the grid during the time 9 to 14 hours. Okay, so these graphs are shown here. So basically, by the use of battery energy storage system, the present graph, that is without a battery energy storage unit is shown, which is shown in a red line, red color graph, that is getting shifted to a green color graph. You can see the change. There almost it is the peak is getting leveling, it is getting clipping. So it is the wave shape is almost during some 11 to say 21 hours. If you look at almost a constant nature, there is some dip, but almost the peak is almost the same. So this is what the advantage we are expecting by implementing this type of battery energy storage system as a direct advantage of the battery energy system. So basically, for charging the battery and taking the energy from the battery. Additionally, as I mentioned in the introductory slide, additional benefits are this is supplying power during the transient period also, and it is capable for maintaining the frequency, voltage, and thereby improving the stability of the system. Okay, so the impact of the battery energy. So this is the example shown here. Particular region is coming around the load. It is not that much high. It is around 150 or 175 megawatt only, and the battery storage comes around 20-25 megawatt. 25 for 3 hours or 20-25 megawatt hour into 3, so around 75 megawatt hour energy storage. So that is only given here. This is the expected shape of the graph with the storage units comes in picture. So the impact of BES in Kerala grid will be specifically the participants are from other sides. I am pointing clearly. The impacts of BES in Kerala grid will be the charge of peak and discharge at charge at off peak and discharge at peak period. So thereby the direct implication is the peak load management, then the frequency stability, variability of solar and wind can be accommodated, as I mentioned, and it's a backup power. And finally, as everything is done in the final consumer side or the utilization side, the transmission line is getting a relief of no need to transmit this amount of power to the load and or the distribution side. Now, if you look at this, there is a possibility of the improvement. The improvement is like here the battery charging is done during the hours where the PV availability is somewhat higher, and based on the charging level, battery level, or SOC level of the battery, this may not be the condition always. If it is very low, then it has to be charged some other times also. It may not be the actual condition. So you cannot say that it has to be charged in between the time during which the PV power is available. It depends upon the SOC level also, because better is to keep the battery in a healthy condition or at a high SOC condition always, so that if any momentary power requirement comes, it can be discharged or taken from the battery. So you cannot say the fixed time, but you can have a control strategy change or control modification in the existing system, battery energy system. If it is integrated to the grid, there can be some control modification, and that control modification we suggested, and we got one paper on IEEE transaction on industrial informatics, and the concept is described here in the coming slide. If I think some of you are is not from electrical background, but I will explain to you each point what the basic physical meaning of this. Even though simply by looking at the diagram, it may not be clear for others. We point out each point related to this. So this is representing our present system or present grid, and present grid is represented by AC grid, and it is supplying loads. And in the present system, almost all the loads are, or majority of the loads are non-linear type of loads. So that is why the shape of the load or the diagram which is connected, which is representing the connected load, is represented by some rectifier type of load, some diode supplying RL load is given. So one side, on the left hand side, you see one AC supplying power to a load. So it is emulating our power system supplying power to the different load. Now in the power system, the point, we have one point where we inject the power from the renewable based power system, and here the renewable based power system is taken as PV plant. PV plant is shown here, and the PV plant is connected to the AC grid. We call that intersecting point as a point of common coupling through a power electronic device, and the power electronic converter is shown here with some 6 number of switches and some capacitor at the DC link side, and the filtering inductor at the output side. That is the interfacing section between the AC side and the inverter side. And if we specifically look at the figure, they are represented, the interfacing inductor are represented by LF, and the inverter switches, it is a 2-level 3-phase inverter with the 2 switches in each limb, and it is handling only 3-phase 3-wire system. So it is not shown, the neutral point is not shown here. Can be applicable for that also if we modify the circuit. And in the DC side of that inverter is supplying the PV power. Directly the PV power can be connected, because the PV power modularity, like it is connected in such a manner that the voltage output is exactly matching with the input voltage of the inverter. So it can be done. Now, additionally, a battery energy storage system, here it is shown as ESS, is also connected to the DC bus through a bidirectional converter here. Bidirectional converter VDC is shown. So this is the power network, power unit, power diagram of the existing system. So the idea is we need to integrate a battery energy storage system to the existing distribution power system, and PV power is also getting injecting power to the present power system. So if this is the case, what we are trying to do is, instead of blindly controlling the charging and discharging of the battery, it is intelligently controlled so that the charging is done on a particular time only, or the charging is done based on some parameters. And discharging time is also, discharging of the battery is also is under control. How the controlling is done, it is explained in one, it is explained by the diagram here. So maybe if I think I will tell you the idea behind this. If specifically some are interested, I can again point out this slide later so that it can be explained in detail. But for others, I think the idea behind this I will tell you. So the point here is, yes. Pardon. Pardon. Not clear. Hello? Is saying anything to me? Hello? Okay.
I'm sorry, I guess it was a mistake.
Okay, right. We'll continue then. So here the idea is the power which is injected to the grid from the battery or the PV power is getting controlled by controlling the 6 switches of the inverter. So the 6 switches are starting from S1 to S6. So we need to control the signals, or we need to control a reference signal generated to control the switches S1 to S6. So that is given at the top, just the top of the inverter, that is S1 to S6. Switching signals are getting generated. It is getting generated by using a hysteresis band current controller. It is a commonly used current controller in the inverter. So it requires the HBCC or the hysteresis band current controller requires a reference current for that. The reference current, how it is generated. So that is what the modification here done here. So that is given by IGABC star. Hope it is clear in the picture. IGABC star is shown, or if you look at separately, it is like a individual current like IGA, IGB, and IGC star. This has to be generated. So if this is getting generated, and if you fix a band for this hysteresis band current controller, then the switching can be done easily by using HBCC controller. So how these reference currents are getting generated? This is getting generated by a theory called instantaneous symmetric compound theory. Instantaneous symmetric compound theory. So basically the controller compute the value which is given in the box, IGA equal to, it is given, the equation is given, and for computing that, the controller gets the information of voltage at the PCC, then the different currents at the PCC. Now if we look at the extreme right of the diagram, the controller diagram, you can see that there are sensors, or there are signals which are coming out from the sensors represented by VGABC, or it is VGA, VGB, and VGC. And there are signals like load current, IL, ABC, or representing the current, individual phase current, load current, ILA, ILB, and ILC. With these voltage and current information, it is computing the load power. The load power, instantaneous load power, can be computed by simply averaging the instantaneous power of each phase, say VGA into ILA plus VGB, then integrating. It is nothing but called a moving average. Those who are working in this area may be aware of that. It is called a moving average. It is simply like a moving average filter. So the average power requirement can be computed. So that is what shown here is instantaneous active power measurement is shown in the block. So it is computed inside the controller by sensing the signal coming out from the current sensors as well as voltage sensors. But the point is, in this controller, there is a flexibility also to control the amount of reactive power taken from the grid to supply the load. So basically, the control structure will be able to control the reactive power means it actually controls the power factor of the individual load, not the total load which are connected here. So the, or in another way, if we look at, you can see that the power factor between the grid current and the voltage, or the power factor associated with the grid current and grid voltage can be exactly controlled. May not be at the unity power factor always, it can be controlled. Because if you look at that aspect, see, if you are controlling unity power factor at all the time, which are doing in most of the inverter presently connected at the PV side of present system, if you are always maintaining the power factor, sometimes the voltage may be high. So it is not specifically controlling the power factor, it is controlling the power factor based on the voltage which is to be maintained at the PCs. Okay, so the power factor can be controlled. So that is controlled by a factor called decided grid power factor is shown here. Decided grid power factor, that is the phi, or tan of that value is used for computing the reference current, which is given here as IGA star, IGB star, and IGC star. And moving forward, I said the instantaneous load power is supplied, but if you look at the position of the inverter connected here, in addition to the load power, the inverter has to do some more function, like it has to inject the power from the PV, it has to control the charging as well as discharging power of the battery. So this also has to be added in the power component in the controller. So in addition to the load power, some other powers like PV, that is the power from the battery, PV, and also power from the battery are added. So these are also to be added, subtracted based on the charging or discharging nature of the battery. Okay, so what I am telling is this can be this can be controlled very easily by using a control algorithm called instantaneous symmetric compound theory. So all the powers are computed. There is one more power called P. L is given, P small l. P capital L is representing the power requirement by the load, and small power is small PL is representing, P small l is representing the power which is used to maintain the DC link voltage, DC bus voltage here. So this power is also required. So these are done in some other type of computation, some other type of control algorithm also. But here the advantage is the power factor as seen by the grid can be exactly controlled by controlling the tan phi, and the additional modification here it is the computation of the PV and how you are controlling the timing for battery charging as well as discharging. Okay, so PB here it is shown like the PB based on heuristic approach is given. So the PB is computed based on some approach, and that approach is described here. That is when battery is to be charged and when it is to be discharged. So in this case, what it is done is the entire time period of 24 hours is divided into different blocks, like morning 6 to evening 6 hours, taking as the normal period of the power system as far as the power demand is concerned, and the peak period is some 6 p.m. to 22 hours, and off peak hours from 22, that is night 10 a.m. to the next day morning 6 a.m. So 3 blocks of time period are taken, dividing as normal period, peak period, and off peak period, and different strategies are followed for these 3 periods. So this is how the computation is done. It is sharing. It will be clear if you look at the picture. The point is this is actually divided into 3 slabs only. This slab only. But in the practical system, you find that you cannot say the demand, even though nowadays for a particular power system like Kerala power system, the demand is from some 6 to or 10 PM, even though it is there. But for a system which is varying in nature, or the load is fluctuating in nature, or if there is a seasonal variation in the load pattern, then you cannot fix the same schedule for all the season of the year. So it depends on many factors. It mainly depends upon the difference between the demand and the generation. The demand and the generation actually fix whether the concerned period is peak or off peak. Based on that, this strategy has to be implemented. So you can go for some advanced method of algorithm where you are finding out the exact time period where there is a matching between the demand and the generation, or you are able to go for some algorithm where you are exactly finding out the time during which the battery is to be charged and discharged. These are simulated and is experimentally verified. It's an experimental setup. I think something is coming from your side. Some queries there. I will explain to you more detail. So this is implemented and it is published. So the basic idea behind this is yes, single stage PV battery grid tied system the PV is directly getting connected to the inverter. That is why it is called a single stage grid tied power system. And power management control is also done based on the grid price information. And the grid price information is actually here we have taken as a fixed rate, fixed value for a fixed time period. It can be enlarged or it can be done with some other type of algorithm so that the overall performance can be improved. We found that in the simulation as well as the actual experimental prototype. This can confirming the system or confirming with the system effectiveness, or there is a solution. Is a promising solution as there is a potential for integrating advanced techniques like machine learning as well as for some other type of optimization when there is a more power source also can be utilized. So this is the idea already I mentioned. Some of the challenges coming in this in the present work is you are actually assuming the battery state of charge, or there are some methods for estimating the state of charge or monitoring or sensing the battery SOC effectively or efficiently, and that can be accommodated in the existing methods also. And the methods for forecasting the solar radiation so that you know exactly whether the solar radiation will be available for charging the battery in the coming days or not, when there is or depending upon the seasonal changes. So all these changes can be accommodated by in the present system, and more efficiency can be achieved. These are the reference. One of the work published in conference, other work published in industry informatics, IEEE transaction, and some data is taken from the Keltron product data. So I will be concluding actually here with the point that the energy storage system is suitably combined, can be useful. It is actually a useful solution for many of the facts. Two facts I explained here by taking the real study, even though it is a real small prototype, by considering the case of a hybrid energy storage system supplying a intermittent type of load or a varying type of load or the dynamic load, and the other case where you have an improvement in the operational efficiency by changing the charging or discharging pattern of the battery. Okay, so with this I conclude. Thank you all for your patient listening. I will be waiting for your questions and interaction. related to this energy storage system. Thank you all.
Thank you, Manoj sir, for your session. It was informative. Participants, now it is the time for interaction, asking questions, doubts, and so on. Please feel free to ask the questions.
Sugesh sir, the majority from electrical background, or?
Yeah, majority is from electrical background, sir, but we also have other branches also. So
Okay.
the questions can be in general. I mean,
Okay,
it will
right.
not be restricted to electrical aspects. It can be anything related to energy storage.
Hello, sir.
Yes.
Hello.
Yes, madam.
Yeah, thank you for this information. But sir, I have a one doubt actually. In
Okay.
your circuit, actually, the battery and the supercapacitor are connected in a parallel with the one only bidirectional device. Actually, one only converter topology. Yes. So how these two behaviors you can control in a parallel branch actually?
Okay, madam. Good. I have presented actually two converter topology for interfacing a hybrid energy storage system with a DC bus.
Yeah,
One
I'm saying it's
topology.
parallel
Yes.
topology.
In one system that is called the active hybrid energy topology, there are two converters. I will
Yeah.
show you. There are two converters, and the two converters are independently controlled. They can be independently controlled. I will show you
Okay.
the slide again.
No, sir, but no. Actually, I know that one, but in your system, which you are shown, is not having that one. It is showing like a two, means one is battery and one is the another branch is the supercapacitor. Yes. That's
Okay,
why.
that is the hybrid topology. That is okay. You are mentioning about the passive hybrid energy topology.
Yeah.
Passive system. There is no control. There is no control. Only the ripples in the load current is getting controlled by the predefined or designed inductor. The inductor which is coming in series with the battery, that is actually filtering out the ripples supplied by the battery. So obviously the load current ripple will be supplied by the other part, the parallel part, that is the supercapacitor.
Okay.
Sir, if you show the circuit and
Okay,
explain,
I
it will
will.
be better.
Yes, I will do that.
Okay, sir. Thank you.
Thank you. This is what is it visible? Sugesh sir, is it visible? Hello.
Yes, sir. Yes, sir.
Yes. This is the topology. I think Madam has asked. Here the topology, the battery current is having a battery VB is having a series inductor LB. So obviously the change of current is getting controlled by the LB, but it has to be designed properly. That is what I said, the demerit of this
So
topology.
totally it depends upon the design of that.
Yes, madam. Correct. This is that is the drawback. There is no control. There is nothing is there. No control for filtering this or these filtering the two currents.
So this inductor will be
Right.
designed on
Thank
the which current ripple? Load current ripples, huh?
Yes. Load current ripples.
Okay, sir.
This is communicated. I think this is done by one of the researcher at IIT. I think not Bhubaneswar or something. One faculty. They only have designed this. Just I am presenting here for the continuation, means many topologies are available like that. Many topologies are there for interfacing this type of hybrid energy storage unit.
Okay, sir. Okay, sir. Thank you.
Thank you.
Hello.
Yes, yes, sir.
Sir, the topology is looking similar to sun active power filter. What is the difference between sun active power filter and this topology?
Okay. Shunt active power filter normally used for AC system. It is interfaced with AC, isn't it?
Yes, sir.
So the inductor is you are saying the inductor which is connected in parallel with that DC or parallel with the AC system.
Sir,
Shunt active filter is actually controlling the active power injected to the AC system or taken by the system by controlling the current. So that is actually used in the AC system. This is the case of a DC. Here also the ripple is actually there. The ripple is actually divided in between the two sources like a battery and the supercapacitor.
Yes, sir.
Yes.
Here additional part is a PV plant and ESS and BDC. That is the additional part looking after.
In which part it is assembling with the shunt active filter? You are saying which
Sir,
part?
the topology in which three-phase three-wire system with the VSI and DC capacitor is present. And the controller is looking like same like controller of shunt active power filter using instantaneous reactive power theory, IRPT.
Okay.
And
the controller, what we discussed for the other type, that is the active topology you are saying. This is the topology. This controller.
Yes, sir, the first diagram in which the whole system, whole topology is present.
Here there is no control, sir. Here there is no control. It is only for transferring the power from the PV side into the battery or to the load. You are controlling S1 or S2. The switches S1 and S2 are controlled. This is what you are saying, sir?
Sir, in slide number 9.
Right. 9. 9 it is. It is
sir,
not 9, I think. It is not 9, I think.
Yes, sir.
One control I mentioned is 15. Control of active topology.
System topology and control heading of that slide.
Anyway, the topology that I mentioned with the combination of two energy sources mainly for DC side. This is everything is integrated with the DC side. So there is no question of this filtering, but you can say it is something like a DC harmonics. You can say it is DC harmonics because here also some pulses or the transient comes means that DC harmonics. So so that is getting arrested actually. You can correlate the nature of the supercapacitor as something like that of the filtering method. Actually, filter per se. But that is the case of AC side. This is the case of DC side. Okay, that is
sir.
Okay, sir.
Thank you, sir.
So, sir, if there is no other questions, then I think we can wind up.
Yeah. Is there any other question? Anybody who wants to ask anything regarding the presented material? Okay, I guess there is no other questions. So we can wind up for today. We had Dr. Manojkumar MV presenting the topic on energy storage. So actually today, according to our schedule, Dr. Uma Shankar of Prince Sultan University was supposed to present, but because of some personal inconvenience, we had rescheduled that talk, and Manoj sir had agreed promptly to be to take the session in between. So I extend my thanks to Dr. Manojkumar MV for the brilliant session here, and answering the questions meticulously raised by the participants. Thank you so much, sir. Thank you so much for joining us. We indeed value your presence in this program. So thanks a lot. And I also thank the participants for being a part of this session for the first day. So today we'll wind up our session. We will continue tomorrow. The link will be the same. Same link. 6 o'clock we'll start this session tomorrow. So we'll be having 2 sessions tomorrow. One session will be the first session will be at 6 o'clock by Dr. Jayaprakash P, who is Director of Technical Education, Kerala. He is a researcher on power electronics and power systems side. So he is a very well-established researcher with a number of publications and so on. So he will be presenting on the grid integration of energy storage. And similarly, we have Dr. Nirmal Mukundan, who will be presenting the second session tomorrow. Dr. Nirmal Mukundan is a researcher at Abu Dhabi. So he will also be a part of the program tomorrow. So I guess we'll wind up